Greetings. Welcome to my video on chi-square test of independence. And in this video and the next one, I'll be doing a couple of examples showing you how the test of independence works out from reading an exercise to figuring out if you have dependence or independence. Now, here we have an example where we have a survey conducted to investigate the relationship between the use of technology in a classroom and the student pass rates. And it's asking us to use a 0.05 significance level to test that claim. Now, from my personal opinion, looking at technology, not use of technology, passing, failing, at this point, I kind of realize, I could predict that I'm going to have to reject the null hypotheses because first of all, this is a dependence-independence problem. It's because this is test the claim that the use of technology and pass rates are related or not. So related means dependent. So we know that this is a test of independence exercise. And from that perspective, I really think that technology and or not use of technology does have an effect on passing and failing rates. So my personal prejudice or my personal experience says that I think I'm going to have to reject the null hypotheses because that's what I think this test is going to show. Well, thank God the world isn't built on the way people feel, think, or their prejudices. It's based on statistics and facts. So let's see what statistics says about this. Now, I know my null hypothesis is the independence statement. My alternative is the dependence statement. And I need to now figure out my second step, which is the test statistics. Well, the good news is that here the test statistics is quite similar to the one on the goodness of fit test, which is basically the sum of O minus E quantity squared divided by E. Now you saw me do this for the test of goodness of fit. If we were to do this for the test of independence, then I would have to create the row sum and the column sums of these rows and columns of this table. And just to show it to you, you would just manually, we're not going to do this manually, we're going to do this on Excel, but I just want to show it to you here, where you would just write the O's like 356, 180, 240, 90, and these will be your O values. And you will then have to find all the row totals and column totals, and I've done that on an Excel sheet. And remember, the way you calculate the expected frequency for the test of independence, let me just recall that you take the row total of the number you're trying to find the expected frequency for, multiply it by the column total, and then you divide it by the grand total. Now you recall that, so for example, if I want to find the expected frequency for 356, I will take the row total of 356. Now the row total of 356 means the sum of the first items in the first row. And I multiply that by the column total of 356. The column total of 356 would be the sum of these two numbers in this column. So that will be called the column total of 356. Divide by grand total. Well, the grand total basically is just the sum of all the values. So it's 356 plus 180 plus 240 plus 90. So the whole thing is the grand total. And that's how you find the expected frequency for 356. Well, same thing, if I wanted to find the expected frequency for 180, I would take the row total of 180, which is the sum of these two numbers. I'd multiply it to the column total of 180, which is the sum of these two numbers. And then I'll divide it by the grand total, which is the sum of all of them. And that's how I'd find every single expected value. And then obviously at the end I add them up. They have to have the same sum, if you recall. And then I can calculate the test statistics by doing O minus E, now that I know what E is, quantity squared divided by E, dragging it down and adding them all up. And that will give me my test statistics. Now that's best shown on a spreadsheet, so let me just erase this so we can actually put the third step here when we get to it and show you how this all works on an Excel sheet. And I have it all set up for you guys. So let's switch screens and let's go to my spreadsheet here. There we go. So I have it all set up for you. I have it's number 11. I have the contingency table here drawn for you. Here's the contingency table. So I have it for you, which means you have to find all the sums, row sums, column sums, and everything. And I have the table here set up. I've written my O's here, and I've added them up. They add to 866. And remember, when you find the E's, all your E's must add up to 866 as well, for you to know you've done it right. And then I'll figure out all the O minus E squares. I'll add them up, and that'll give me the test statistics. Well, let's see how I'm going to do that. So I'm going to say for 356, I'll take the row total of 356, which is 536, multiply it by its column total, which is 596, and divide it by the grand total, which is 866. And that will be the expected frequency for 356. Now let's calculate the expected frequency for 180. It will be the row total of 180, which is 536, multiplied by a column total of 180, and divide by the grand total. Let's do it for 240. Row total. Oops, I clicked on my drawing. Let's try that again. Okay, so for 240 will be the row total times the column total, divide by the grand total. For 90, it will be the row total of 90, which is 330, multiplied by the column total of 90, which is 270, divide by the grand total, which is 866. And there's all my expected frequencies. Now, here's, I start praying and I'm saying, oh God, please let this number be 866. Oh, thank God it is. So that means I've calculated my expected frequencies properly. Now we move on to calculate the test statistics here. So the first one will be O minus E, quantity squared divided by E. So there's that. I think these circles are going to give me trouble, so let me just get rid of them. So when I'm clicking on them, it won't give me the wrong thing. So I get say equals, parentheses, O minus E to the power of 2 divided by E. And you know I don't have to do that, right? There we go. You're absolutely right. I do it once, I drag it down, and it does it for the rest of it. So same here, let me drag it sideways, and there is my test statistics. So if I wanted to write the test statistics, say there, I'll just tap on that number. There's my test statistics for that exercise, which is 3.789 or 3.79. So that becomes my test statistics. So let's go on to my lecture again, and let's look at this. All right, so now I've calculated the test statistics, and we all saw how it was done. Let's write the value, and let's say use 2 decimal places. So it'll be 3.79, and that is my second step. So all that was to just do the second step. Okay, now the third step, as again we all recall, it is a chi-square distribution, and it's a right tail, because everything for the test of goodness of fit and test of independence will be the same rejection region. And that's one very nice thing about this new chapter on multinomial experiments with these two tests, is that for both of them, the third step is always a right tail chi-square distribution, and it's never left tail or two tails. So that's really nice. It takes away the number of things we need to choose as we go through it. So then that becomes my rejection region. So let me, as always, I want to make sure that our eyes really catches the rejection region when we look at it, so you know exactly when to reject and fail to reject, because as you recall, it all has to do, your rejection or failure to reject, that final decision, all has to do with whether the test statistics lies in this red area or not. And as you know, if it does, then you're going to have to reject the null hypothesis. And if it doesn't lie in the red area, then you fail to reject the null hypothesis. So that's why this red area is very important for us visually, to make sure that if we're there, that means we're going to reject. And if we're not there, we're going to fail to reject. Well, in order to figure out if we're there or not, obviously I need to know what that point is. Now remember, this is a chi-square distribution. This point here is 0. There are no negative values here. Alpha is 0.05, so that's always necessary when I'm finding critical values. Okay, so alpha is 0.05. Now, the command, verbatim to what you did for the goodness of fit test. We're going to do the chi-square dot inverse dot right tail, and then you're going to put alpha and the degrees of freedom. Now remember that alpha here, and also for the test of goodness of fit, is always what alpha is. You never have to touch it. You never have to divide it by 2. You never have to do anything to it. So whatever the problem tells you, that's what you put in a formula here, which is 0.05, or the command. And the degrees of freedom, now, for the goodness of fit, it was k minus 1, but for the test of independence, remember it was r minus 1 from your reading and from watching the intro video, was c minus 1, where r is the number of rows and c is number of columns. So you have 2 rows and 2 columns, and 1 times 1, so your degrees of freedom is just 1. So the command will be chi-square inverse right tail 0.051. So let's go ahead and do that again on Excel to just see how I can type that up. So let's just come here and do it. So CHISQ chi-square inverse right tail, probability 0.05, and degrees of freedom was 1, and it gives me 3.841. So the critical value is 3.841 is my critical value. 3.841. I can erase this now. And you know what? Since I used 2 decimal places for my test statistics, why don't I just use 2 decimal places for my critical value as well? So instead of writing 3.841, I could just write 3.84. Doesn't really make a difference. So let's see. Now, so that's my step 3. So there's my step 3. Now step 4, as you recall, is a decision that you're going to have to make and a conclusion you're going to have to come up with. So decision, the test statistics here, 3.879, now that falls shy of the rejection region, and it got saved, so it didn't go into the rejection region. Well, got saved or not has to do with perspective. But anyways, it doesn't fall in a rejection region, so you fail to reject the null hypothesis. So that means the null hypothesis is we're failing to reject it is good. So wow, that means that the test shows independence. So you see, statistics shows, now we believed that technology makes a difference. So it affects the passing and failing rates. So we thought the test is going to come up with the final result of a dependency. But you notice that it fails to reject independence, which means the use of technology is not dependent or is not related to pass rate or fail rate. So we can just write there independent. There's no proper or any set way of saying the conclusion here, unlike what you noticed in the 1 and 2 population testing, where there was a specific way of saying things. And also in the previous one, in the goodness of fit, there's also a specific way of saying things. Probabilities are distributed as expected, or they're not distributed as expected. But for the test of independence, you basically just pretty much say, are they independent or dependent? I mean, you could actually write a paragraph saying the test shows that, I don't know, pass rates and technology are not dependent. Okay, so whatever. So that's just your personal preference or whoever is asking you to do it. Now here's how we do a 4-step test of independence. Thank you.